Hello everyone. Good afternoon to one and all. So welcome to this lecture number 6 of this chapter, combined stresses. Okay. And in the previous lecture we have seen few numericals based on this shear force diagram and bending moment diagrams. Okay. So again here in this lecture we are going to see one more numerical based on this SFD and BMD diagrams. Okay. So we will see one more variety of the numerical here. So write down this numerical. Compute a shear force and bending moment at critical points and plot SF and BM diagram, that is shear force and bending moment diagrams, for the beam as shown in figure. Okay, so this is the beam as shown in figure. So here this uh, overhanging beam is given here because this beam is supported at point A and at this point D. Okay, and after this, from D to this E, this beam is overhanged here. Okay, so this overhanging beam is given and it is supported at A and at point D. At A it is fixed support and at point D it is roller support. Okay, so also 30 kilonewton force is vertical load is applied at point B here. Okay, which is from 2 meter from the distance from A. Okay, also from this C to D, a uniformly distributed load is given. Okay, whose intensity is 10 kilonewton per meter. Okay, UDL is given here from C to D. Okay, and from D to E again uniformly varying load is given. Okay, and whose intensity is 15 kilonewton per meter, uniformly varying load. Also, one inclined force is given here, or inclined load of 10 kilonewton is given at point E. Okay, at an angle of this 40 degrees. Okay, at an angle of this 40 degree, one inclined load 10 kilonewton is given here. Okay, now again here what we have to do, we have to calculate all the shear force and bending moments of at all critical points, that is from at point A, at point B, C, D, as well as at point E, and we have to draw a shear force and bending moment diagrams here. Okay, so therefore draw this figure, then we will solve this numerical step by step. Okay, now we will see here. So as we seen in this previous numericals, where this uniformly distributed load is given, and here here from D to E uniformly varying load is given. Okay, so therefore first of all we have to convert this uniformly distributed load into a point load, and this uniformly varying load into a point load, and we have to find out the location of this uniform point loads, these different point loads. Okay, so therefore first of all we will find this point load, we will convert this uniformly varying load into a point load. Okay, so convert this uniformly varying load into a point load. So therefore this point load, as we know, this point load is equals to area of this triangle. Okay, area of this triangle. So therefore one half, it is one half into base of this triangle, that is this 15 kilonewton per meter it is given. Okay, and height of this triangle, that is 3 meter here. Okay, so therefore this point load is equals to one half of this 15 into 3. Okay, so calculate this point load. So therefore this point load will become 22.5 kilonewton. Okay, this 22.5 kilonewton point load will act somewhere here. Okay, it is 22.5. Okay, then after this similarly convert this uniformly distributed load into a point load. Okay, so this UDL into point load will be, this point load is equals to this intensity of this uniformly distributed load, that is 10 kilonewton per meter, into this length of this beam, okay, on which this UDL is applied. Okay, so therefore this 10 kilonewton into this 4, so it will become 40 kilonewton, this point load 10 into 4. Okay, the point load is equals to 10 into 4, and this will act at the center of this beam here. Okay, it is 40 kilonewton at the center of this beam. Okay, Then after this, again what we will do, here one 10 kilonewton inclined load is given. Okay, 10 kilonewton inclined load is given. So therefore we have to convert this 10 kilonewton inclined load into two components. One, it is horizontal component, and second one, it is vertical component. Okay, we will resolve this 10 kilonewton force into two components, one horizontal and vertical component. Okay, so here we can say this 10 kilonewton load will be converted into this two horizontal and vertical components here. Okay, so this angle of inclination is given 40 degree. Okay, so therefore this horizontal component will be 10 kilonewton, this 10 into cos of this 40 degree. Okay, this horizontal component will be 10 into this cos of 40 degree, and this vertical component will be this 10 kilonewton into sine of this 40 degree. Okay, 10 sine 40, and here this horizontal component will be 10 cos 40. Okay, so therefore here one more vertical component will be there, it is 10 sine 40, this 10 sine 40. Okay, now after converting all these loads into a point load, this inclined load into vertical load, this uniformly varying load into a point load, and this uniformly distributed load into this point load. Okay, now we have to calculate the support reactions at A and at D. Okay, so we have to calculate the support reactions at A and D. Okay, next step. So therefore step number 1, calculate the support reactions. So RA and RB. So there are two criteria by using we can calculate these support reactions. Okay, and these two criteria are, first one, it is take the summation of the moments of all the forces, summation of the moments due to all the forces about any one support. Okay, so here what we will do, we will take a moment about A. Okay, about this A support, and we will equate it to the 0. Okay, so this will be the sign convention. This clockwise movement will be considered as a positive, and this anti-clockwise movement will be considered as a negative. Okay, so therefore here it is also one force is there. Therefore what we will do here, so we will take moment of all these forces about this A is and equate it to the 0. Okay, so therefore this RD, okay, this RD will try to rotate in anti-clockwise direction about this point A. Okay, so therefore it will be minus. Okay, so therefore this RD into this distance, so 4 meter plus this 2 meter, 6 meter, plus again this 2 meter, that is total 8 meters from this point A. Okay, this RB distance of this RD, so minus of RD into 8. Okay, minus of this RD into 8, because this RD will try to rotate in anti-clockwise direction. Okay, now this 30 kilonewton, okay, this 30 kilonewton, okay, after that this 10 sine 40 degree. Okay, this 10 sine 40 degree will try to rotate in clockwise direction. Okay, this will try to rotate in clockwise direction. So therefore this will be plus. Okay, so plus this 10 sine of 40 degree. Okay, 10 sine 40 into this perpendicular distance, that is 3 meter plus this 4 meter, 7 meter plus 2 9 plus 2 11. Okay, so that means this 10 sine 40 degree into this 11. Okay, after that this 40, so 22.5 kilonewton load. Okay, this 22.5 kilonewton load, so again it will try to rotate in clockwise direction, so it will be plus, moment due to this will be plus. So 22.5 into this distance, okay, that is this 2 plus 2 4 plus this 4 8, this 8 meter, and this distance will be 1 meter. Okay, this distance will be 1 meter here. Okay, so that is 4 8 plus 1 9. Okay, 22.5 into 9. Okay, after that this 40 kilonewton load. Okay, so plus again this 40 kilonewton load will try to rotate in clockwise direction. Okay, it will generate a movement into a in clockwise direction. Okay, so therefore this 40 into this 2 plus 2, and again this will be at a distance of 2 meter here. Okay, this distance will be 2 meter here. Okay, so 2 plus 2 plus 2 6. Okay, 40 into 6. Then again this 30 kilonewton will try to rotate again in clockwise direction. Okay, so therefore it will be plus this 30 kilonewton into this distance, perpendicular distance, that is 2 meter. Okay, plus this 30 into 2, and summation of all these moments is equals to 0. Okay, then again simplify this equation. Okay, after simplifying this equation we will get the value of this RD here. Okay, so therefore this RD is equals to 71.65 kilonewton. Okay. Calculate this RD, 71.65 kilonewton. Reaction at point D here. Okay, RD. Now again, next thing is there is that, so we will use the second criteria, that is summation of all the vertical forces equals to 0. Okay, second criteria. So summation of Fy is equals to 0 here. Then again we will consider this upward side forces will be considered as a positive, and this downward side forces will be considered as a negative. Okay, so by using these sign conventions, again we will take this summation of all the vertical forces here. Okay, so therefore this RA, okay, RA and this RD are going in the upward direction, so RA plus RD, these two forces will be positive, RA and RD. Okay, then again this 30 kilonewton, this 40 kilonewton force, this 22.5 kilonewton, and this 10 of sine 40 degree. Okay, all these forces are in the downward directions. Okay, so these will be minus. Okay, so therefore this minus 30. Okay, this minus 30, then again this minus of 40 degree, sorry, minus 40 kilonewton force. Okay, then again minus 22.5, this due to this universal bearing load. Okay, and minus of 10 sine 40. Okay, this minus of 10 sine 40, it is due to this inclined load 10 kilonewton. Okay, so summation of all this is equals to 0. Put the value of this RD, 71.65 kilonewton, here in this equation. Okay, RD is equals to 71.65 kilonewton. Okay, and calculate this RA. Okay, find out the RA. Yes, tell me the value of this RA.
27.27.
RA is equals to 27.27, because RA plus RD is equals to 98.93 kilonewton. This 98.93 minus this RD, that is 71.65. Okay, so that we will get the value of this RA. Okay, now next, after calculating these support reactions RA and RD. Okay, so next thing that we have to calculate the shear forces. Okay, shear force calculation, step number 2. Okay, so therefore at this point A, first of all we will find out the shear force at point A, at point B, at point C, then again at point D, and at last at this point E. Okay, so, so before calculating this again shear forces, so we have to consider this sign convention for the shear force calculations. Okay, so upward force at the left side of this left side of the section, and downward force at the right side of this section will be considered as a positive, and downward force at the left side of the section and upward force at the right side of the section will be considered as a negative here. Okay, so by using these sign conventions, again here we will calculate the shear force at these different critical points. Okay, so therefore the shear force at point A, so first is shear force at point A is equals to at this point. Okay, so therefore shear force at point A is equals to this RA. Okay, RA, and this RA is equals to 27.28 kilonewton. Okay, so this value of this RA support reaction is equals to 27.28 kilonewton. So therefore this shear force at point A will be this force. Okay, now next, now shear force at point B here. Okay, next thing is that shear force at point B. Okay, but from this A to B there is no additional extra load, there is no point load or no universally distributed or universally varying load is there. Okay, so therefore this shear force will be remain constant from A to B. Okay, from A to B shear force will remain constant. Okay, so therefore when we will take a section at B, okay, the shear force will be, okay, shear force at point B is equal to this force, okay, plus this A. Okay, when we take a section here, okay, so shear force will be A, that is RA. It is positive because it is going upward and it is at the left side of the section. Okay, and this RB, it is going downward and it is at the left side of the section. Okay, so here this left going downward force at the left side of the section will be considered as a minus negative force. Okay, so therefore here this force will shear force at point B is equals to 27.28, that is RA, minus this 30. Okay, this RA minus this 30. Okay, so this will become minus 2.72 kilonewton shear force at point B. Okay, now after this, so what we have to do, we have to take a section at the just left side of the C. Okay, just left side of the C, but there is again no load between this B to C. Okay, between from this B to C again there will be no load. Okay, so therefore shear force will be remain same, that is minus 2.72 kilonewton from B to C. From this B to from point C, the shear force will remain constant. Okay, so therefore we will take a section just at the right side of the C. Okay, we will take a section here and we will calculate the shear force at point C. Okay, at up to at point C the shear force will remain same, that is minus 2.72 kilonewton up to C. There is no additional load. So therefore next the shear force at point D is equals to, after this C, the shear force at point D. So therefore again we have to take this two sections. One is just at the left side of this D, point D. Okay, and second section at the just right side of this point D. Okay, when we take a section at the just left side of this point D, okay, the shear force will be this RA, it is going upward direction, so it is plus. Okay, this 30 kilonewton is minus, then again this 40 kilonewton. Okay, 40 kilonewton at the center of this CD. Okay, and it is again going in the downward direction. Okay, so again it will be the minus. So therefore this 27.28 minus of this 30 minus 40. Okay, so therefore the shear force at point D, when we take a section just at the left side of this D, it will be minus 42.72 kilonewton. Minus 42.72 kilonewton. Okay, shear force at point D when we take a section just at the left side of this D. Now after this we will take a section just at the right side of this D. Okay, here we will take a section at the just right side of this section D, and again we will calculate the shear forces. Okay, so therefore shear force at point D, when we take a section just at the right side of this D, okay, then at this condition this RA, it is in going in the upward direction, as well as this RD here at point D, okay, it is again in the upward direction. Okay, so this RA and RD will be positive, this 30 kilonewton will be negative minus, and this 40 kilonewton, okay, it is due to this universally distributed load, and again it is in the downward direction, so it will be minus again. Okay, so therefore shear force at point D, when we take a section at just right side, okay, it will become this 27.28 force. Okay, that is this RA, it is plus, then this 30 kilonewton, it is minus. Okay, then again this 40 kilonewton, Okay, this 40 kilonewton is minus again. Okay, then again this RD plus this RD. Okay, plus RD is equals to this 71.65. Okay, then calculate this shear force at point D. It will become this 28.93 kilonewton plus 28.93 kilonewton. It is going in the upward direction. Okay, simultaneously you must have to write down all these equations and values. Okay, so after calculating the shear force at point D, we have to calculate the shear force at point E here. Okay, so therefore what we will do, we will take a section at point E here. Okay, and the shear force at point E is equals to this. When we take a section at this left side of this E, this is the force, downward force, that is 10 kilonewton, 10 sine 40 degree. When we take a section at just left side of this E, okay, this 10 sine 40 degree is the force and it is in the downward direction and at the right side of the section. Okay, the force which is moving in the downward direction and at the right side of the section will be considered as a positive. So therefore here shear force at point E is equals to plus of 10 sine 40. Okay, plus 10 sine 40 degree, which is equals to plus 6.43 kilo Newton shear force at point E.
Yes, sir.
Okay, now after calculation of this shear force, next step number 3, we have to calculate the bending moments. Okay, here step number 3, bending moment calculations. Again we have to consider this shear bending moment sign convention here. Okay, this clockwise movement at the just left side of this section and this anti-clockwise movement at the right side of this section will be considered as a positive. Okay, and this anti-clockwise movement in the left side of the section or in this clockwise movement at the right side of the section will be considered as a negative. Okay, this bending moment sign convention already we have seen in the previous numericals as well as. Okay, so therefore we will calculate the shear bending moments at these critical points, that is A, B, C, D and at point E. Okay, so as we know this bending moment at point A is equals to 0, MA is equals to 0 because this at point A this is a simply supported beam, sorry, overhanging beam, and this at point A it is fixed hinge support is given. Okay, so bending moment will be 0 here. Okay, so again bending moment at point E will be 0 because it is a overhanging beam. Okay, overhanging beam, and at the free end of this overhanging beam bending moment will be 0. Okay, so MA is equals to 0, moment at A is equals to 0, moment at E is equals to 0 because it is a overhanging beam. Okay, this is because of the simply supported beam. After this, we will calculate the bending moment at point B, at point C and at point D. Okay, so therefore bending moment at point B is equals to, at point this B is equals to, so therefore take a section at point B here. Okay, at point B, so bending moment at point B is equals to, either you have to consider this left side of this beam or right side of the beam. Okay, so we will consider left side of the beam because only one force is there at the left side of the beam. Okay, when we take a section at point B, so this RA, okay, this RA which is equals to 27.28. okay, and this will try to rotate in clockwise direction. Okay, it will try to rotate in clockwise direction and it is at the left side of this section, so this will be positive, it will be considered positive. So this 27.28 RA into this perpendicular distance, that is this 2 meter here. okay, into this 2. So therefore this bending moment will be plus 54.56 kilonewton meter. Bending moment at point B will be this 54.56 kilonewton meter. After calculating this bending moment at point B, now we will calculate the bending moment at point C here. Okay, so therefore take a section at point C. Take a section at point C. Consider this left side of this beam. Okay, so this RA will try to rotate in clockwise direction. So RA into this perpendicular distance from this C is equals to 4. This 2 plus this 2, 4 meter distance from this C. Okay, so RA into 4. Okay, so here moment at C is equals to 27.28 into 4. This 27.28 is RA into 4. Okay, then after that this 30 kilonewton will rotate in anti-clockwise direction at the left side of this beam. Okay, so at the left side of this cross section, this anti-clockwise movement will be considered as a negative. So minus of 30 kilonewton into perpendicular distance, that is 2 meter here. Okay, so minus 30 into 2. Okay, minus 30 into 2. So calculate this 27.28 into 4 minus 30 into 2. It will be 42.12 kilonewton meter. 42.12 kilonewton meter. Then after this bending moment at point D. Okay, so therefore take a section at point D here. Take section at point D. Okay, and consider the right side of this beam, because only two forces are there at the right side of this beam. So it is 10 sine 40 degree, and this 22.5 kilonewton point load due to this universally varying load. Okay, so bending moment at D, MD is equals to this 10 kilonewton force will try to rotate in clockwise direction, and it is at the right side of the section, as well as this 22.5 kilonewton force will be again try to rotate in clockwise direction. Okay, and it is at the right side of the section, so both these moments will be negative. Okay, so MD is equals to minus of this 10 sine 40 degree into perpendicular distance, this from D to E it is 3 meter. Okay, so this 3 meter, so it is 3. Okay, then again this 22.5 kilonewton load will try to rotate in anti-clockwise direction, so it is minus. So this minus of 22.5 into this 1, that means distance from D to this load. Okay, so it will be the 1 meter. Okay, calculate this. So you will get the value of this bending moment at point D is equals to 40 minus 41.76 kilonewton. Minus 41.76 kilonewton meter. After calculating this bending moment at different these critical points, so we have to draw a SFD and bending BMD diagrams. Okay, so here we will draw a shear force diagram. Okay, so therefore shear force at point A is equals to 27.28 kilonewton. Okay, so first of all we will draw a horizontal line. Okay, we will draw a horizontal line. So at point A here the shear force is plus 27.28 kilonewton. So here this plus 27.28 kilonewton, mark this point. Okay, mark this point 27.28 kilonewton. Then after that shear force at point B. From A to B there is no additional load, so shear force will be constant from A to B. So horizontal line will be there. Okay, constant shear force here. Okay, then again at point B here the shear force is minus 2.72 kilonewton. Okay, so therefore from this value from this 27.28 kilonewton. Okay, this shear force at point B is minus 2.72 kilonewton. So mark this point here, 2.72 kilonewton at the downside of this horizontal line. Okay, join these two points by a straight line because only point load is there at point B. So this shear force will be constant. Okay, then again from B to C there is no additional extra load. Okay, from B to C. So from B to C again the shear force will be constant. So horizontal line will be there here. हॅलो, कुणाचा तरी माईक ऑन आहे बघा, माईक ऑफ करा. Okay, so from point B to C no additional load is there, so shear force will be constant from B to C. So horizontal line will come here from B to C. Again from this C to D, okay, this shear force at D is equals to minus 42.72 kilonewton. Okay, the shear force at point D is minus 42.72 kilonewton. So first of all locate this point, minus 42.72 kilonewton. Okay, and from C to D uniformly distributed load is there. Okay, from C to D this uniformly distributed load is there, so the shear force will be straight line. Okay, again it will be straight line, and it is by join these two points C and D by a straight line. After this again this shear force at point D is equals to this 28 plus 28.93 kilonewton. Okay, so look at this point here. Then again join these two points by a straight line. Then after this shear force at point E is equals to this plus 6.43 kilonewton. Okay, so it will be somewhere here. It is wrongly the shear force. Locate this point here, plus 6.43 kilonewton. Okay, and from D to E here in this given beam, from D to E uniformly varying load is given. Okay, uniformly varying load. So therefore in this diagram it will be the parabolic curve. Okay, from D to E join these two points by a parabola, and from D to E again this vertical straight line will be there. Okay, this is our shear force diagram. So after this similarly plot a bending moment diagram. So moment at A and moment at E is equals to 0. So draw one horizontal line here. Okay, locate moment at MA. Here MA is equals to 0. This moment at E, ME is equals to 0. Okay, locate the moment at B. This MB is equals to plus 54.56 kilonewton. The moment at B is equals to this. Locate this point. 54.56 kilonewton meter. Then moment at C is equals to 49.12 kilonewton meter. Locate this moment at CMC. This will be at 49.12 kilonewton meter. And moment at D is equals to minus 41.76 kilonewton meter. It is. So locate this point, minus 41.76 kilonewton. It is just below the horizontal line. Okay, and now join all these points from A to B. Okay, from A to B, the shear force is constant, so bending moment will be again a straight line here. Okay, join these by two straight lines. Again from B to C there is no additional extra load, so again shear force will be constant here, so straight line bending moment will be straight line. Okay, then from C to D, okay, here this constant load is given, universally distributed load, uniformly distributed load. Okay, so therefore here parabolic curve will be there in bending moment diagram, so join these 2 points by a parabolic curve. And from D to E, uniformly varying load is given. Okay, so therefore in the bending moment diagram it will be a cubic curve. Okay, join these by a cubic curve. So this will be our a bending moment diagram. So this is our overall shear force and bending moment diagram. Now we will see one more numerical here. Okay. Draw shear force and bending moment diagrams SFD and BMD for this given beam as shown in figure. Okay, so this AB, it is a simply supported beam is given. Okay, and this beam is just rested at these A and B points. Okay, then 100 kilonewton load is given at point C here, which is 2 meter apart from this A. Okay, then again at point D, which is 4 meter apart from A, or we can say 2 meter apart from this C. Okay, one couple is given, that is 60 kilonewton meter clockwise couple is given at point D. Similarly at point E, again one clockwise 50 kilonewton meter clockwise couple is given here, which is 3 meter distance from this D. Okay, so draw this figure and try to solve this numerical. So step number 1, calculation of the support reactions. So this beam is simply supported at A and B. Okay, so therefore we will calculate the reaction at A, RA and RB. Okay, by using these two criteria, that is summation of all the forces in the vertical direction is equals to 0, and by using this second criteria, that is summation of all the moments about any one support reaction or support, that is A, is equals to 0. Okay, so here summation of all the forces, vertical forces, is equals to 0. So RA is plus, this RB is also plus. Okay, and this 100 kilonewton, it is minus. So minus 100 plus RA plus RB. So RA plus RB is equals to 100. This is our equation number 1. Okay, use the second criteria, that is summation of moment of all the forces about this point A is equals to 0. So therefore this 100 into this 2 kilonewton, sorry 2 meter, 100 into 2. Okay, then again here moment at D is given, as well as this moment at E is also given, 60 kilonewton and 50 kilonewton meter respectively. Okay, and both these new moments are in clockwise direction. Okay, so therefore we will add these two moments. So because clockwise moment here is considered as a positive and anti-clockwise moment is considered as a negative moment here. Okay, so therefore this 100 into 2 plus this 60, this 60 kilonewton will be directly added here, plus 50, this 50 kilonewton, and this minus of this RB into this 2 plus 2, 4 plus 6, 10 meter. Okay, minus of RB into 10, because this RB will try to rotate in anti-clockwise direction about this point A. Okay, so therefore this minus RB into 10. To simplify this equation, we will get the value of this RB here, 31 kilonewton. RB is equals to 31 kilonewton. Put this value of RB here in equation number 1, we will get the value of RA, that is 69 kilonewton. Calculate the support reactions RA and RB. Okay, this is our step number 1, calculation of the support reactions RA and RB. After calculating these support reactions, step number 2 is calculation of the shear forces. Okay, step number 2, shear force calculations. So again, this sign convention, we will consider this sign convention for the shear force calculations. Okay, so shear force at first of all, shear force at point A is equals to, this shear force at point A is due to this support reactions RA, and RA is equals to 69 kilonewton. Okay, shear force at A. Shear force at C is equals to, because from A to C this will be remain same, shear force will remain same or constant from A to C, because there is no additional extra load is there in between this A to C. Okay, therefore this shear force at point C is equals to, this 100 kilonewton will be added. Okay, and it is in the downward direction. Okay, so this 69 minus of 100. Okay, we will take a section just at the right side of this C. Okay, this 100 kilonewton is going in the downward direction, so it will be minus, and this RA is in the upward direction, it will be considered as a plus. This RA 69 minus this 100, it will become minus 31 kilonewton. Okay, shear force at point C. Next, from C to D, no any extra load is there. Okay, so therefore shear force will remain same from C to D. Okay, shear force will remain same or constant from C to D. So therefore shear force at point D is equals to shear force at point C. Okay, shear force at point D is equals to shear force at point C. So therefore it will become minus 31 kilonewton, as there is no load between this C and D. Okay, C and D. Also from D to E, again there is no load. Okay, therefore shear force will remain same from D to E. Again shear force at point E is equals to, again it will be minus 31 kilonewton, same shear force will be there. Okay, from E to B, again no additional extra load is there, so shear force will remain same from E to B, and at point B this RB will, again we will consider this RB, so shear force at point B is equals to, again it will remain same, and this RB is equals to minus 31 kilonewton reaction at B, so this will be again minus 31 kilonewton. Okay, so after calculating this shear forces at all these critical points, next step is step number 3, calculate the bending moments. Bending moment calculations. Okay, so bending moment at point A and bending moment at point B will be 0. Okay, MA and MB is equals to 0, because this beam is simply supported beam, and the bending moment will be 0 at the supports. Okay, so therefore MA is equals to MB is equals to 0. as it is simply supported beam and it is simply rested at these 2 points A and B. So bending moment will be 0 at these 2 points. Okay. After this, calculate this bending moment at point C. Next, point C, point D, and point D. Okay. So therefore, take a section at point C. Here, take one section at this point C. Okay. Consider the left side of this beam. So bending moment at point C is equals to this RA will try to rotate in clockwise direction at the left side of this section. Okay, so it will be plus. So this RA is 69 kilonewton into this perpendicular distance, that is 2 meter. Okay, so bending moment at C is equals to this plus 69 into 2, which is equals to 138 kilonewton meter. Okay, here this is at the left side of this section and it is rotating in clockwise direction, so it will be considered as a plus, positive. Okay, next, bending moment at point D. So take a section at point D here. Okay, take a section at point D. So this RA into this 2 into 2, 4 meter. Okay, this RA into 4 is positive, 69 into 4. Okay, then this 100 kilonewton. Okay, this 100 kilonewton will try to rotate in anti-clockwise direction. So this will be minus of 100 into this perpendicular distance, that is 2 meter. So minus 100 into 2. So when we take a section at the just left side of this point D. Okay, section at left side of the point D. Okay, so this will be 76 kilonewton meter. When we take a section at just right side of this point D, when we take a section just at the right side of this point D, so this RA into this 4 meter minus this 100 kilonewton into this 2 meter plus this 60 kilonewton moment. This 60 kilonewton moment is directly given here, so we will consider that as well as. Okay, this 76 kilonewton plus this 60 kilonewton, it is in the clockwise direction. Okay, at point D. So it will become 136 kilonewton meter when we take a section at just at the right of the point D. Okay, after calculating this MD, so bending moment at point E next. So therefore consider one section just at the left side of this E, taking a section at left side of this point E. Okay, so this 69 into this 7 meter. Okay, this 2 plus 2, 4 plus this 3 RA into this 7 meter distance, it 69 into 7. Then this 100 into 2 plus 3, 5, it is minus this 100 into 5. Okay, plus this 60 kilonewton moment at point D, plus 60 here. So this bending moment at point E will be 43 kilonewton meter when we take a section just at the left side of this E. Similarly, take a section at the right side of this E, calculate the bending moment. Okay, so this, when we take a section at the just left side of this E, bending moment ME will be 43 kilonewton meter. Okay, so this 43 as it is. Okay, plus this 50 kilonewton movement at point E. Okay, it is in the clockwise direction, so add this 50 here kilonewton, so this will be 93 kilonewton meter movement at point E. Okay, and bending moment at point B is equal to 0 because it is simply supported beam. Okay, after calculating all these values of this bending moment, shear force and bending moment values, so next step is we have to plot shear force and bending moment diagram. Okay, so here at point A, while drawing a shear force diagram at point A, value of this shear force is 69 kilonewton here. Okay, so plus 69 point, mark this point, plus 69 here. Okay, then after this, shear force at point C is minus 31 kilonewton. Okay, from A to B it is constant. So therefore from A to B the shear force is constant. Okay, and shear force at point C is minus 31 kilonewton. So mark this point minus 31 here. Then join these two points by a straight line. Okay, and from this C to point D there is no additional extra load is there or in between this CD or DE or E to D. Okay, so therefore shear force will remain same or constant. So it will be minus 31 kilonewton from C to D, and at point D it is again minus 31 kilonewton. So join these 2 points and draw SFD. Similarly, draw bending moment diagram. So moment at A is equals to 0, moment at D is equals to 0, MA and MD is 0. Okay, moment at B is 1.38 kilonewton, 138 kilonewton meter. Okay, so mark this point. Okay, here MA is equals to 138 kilonewton, sorry MC. MD is equals to 76 kilonewton when we take a section at just left side of this D, and when we take a section at right side of this D, we will get the value of moment at D. MD is 136 kilonewton. Okay, so mark these 2 points, 76 kilonewton and 136 kilonewton. Okay, similarly moment at E is 43 kilonewton and 93 kilonewton, these 2 points. So join these, plot these 2 points. Okay, and join all these 2 points by a straight line. Okay, this is our bending moment diagram. Okay, so इथपर्यंत कोणाला जर डाऊट असेल तर विचारा, otherwise we will stop here and in the next lecture we will start new chapter. कोणाला काय डाऊट आहे काय?
No, sir.
Okay, then we will stop here